It's a good thing that really wasn't much of a lesson. Wait till yeah, totally. Okay. I'll figure this out. Let's try again. Okay. Okay, so let's start with kind of the fulcrum of what we're doing in physics. Physics, in a way, is applied math. You need to have pretty impeccable math skills. Like, your algebra has to be solid, because I showed you guys, you've already got a copy of that formula sheet, right? There's a lot of formulas on there. And you need to be able to rearrange those pretty much like that. Like, it needs to be a fairly comfortable sort of thing where you know how to do your math. But the big difference between math and physics is that we need to do some sort of measurement. I use these terms a lot in my chemistry class. We're going to do, I did it wrong again. The study of physics is not qualitative observations. Someone correct me, which one is it? It's going to be quantitative observations. I can't believe that's still wrong. It was wrong last year too. Okay, so if you don't know that word, first of all, I didn't do a good enough job teaching you in the past. A quantitative observation involves a quantity, right? But not just a number, it involves a unit of some type, possibly even a direction. So everything we need to do here, you need to change your mindset here. If you write a number down and you don't have a unit behind it, expect me to take the mark off. It's the same thing I done in chemistry. We don't just focus on numbers. We don't just do 7 plus 5. It's 7 kilometers plus 5 kilometers, or it's whatever the units happen to be. So make sure that you always include some sort of unit. So here are some of the main units we're going to work with, but these are by no means the list. We're going to talk about length, how long something is. Standard unit is a meter. Now, that being said, there are other ways of measuring. For example, we can measure things in kilometers, km, or maybe it's a small unit of measurement. Maybe like a centimeter, or a millimeter, or I put an N in front. Anybody know what N stands for? Nanometer. Yeah, this is like the size of an atom small. Right? So same sort of thing with the rest of these units. You can always throw a prefix in front of all of them. This one already has one, actually. A kilogram actually is 1,000 grams. The base unit of temperature is actually kelvins, not Celsius. We'll measure things in time, and I'll move on. You guys don't actually need to talk about this one at a time. So here's the next slide to talk about that. I need you guys to know how to convert between unit types. So maybe you've seen this picture before somewhere. It's like a staircase, right? So as you go up the staircase, it means you're getting to bigger and bigger units. A kilo is a lot of something, right? A kilo is 1,000 of something. A hecto is 100 of something. Whereas if you have centas and millas, they're smaller units of measurement. Essentially, you're either timesing or dividing by 10. You just need to figure out which way to go. Here's another chart that is even more comprehensive. It kind of goes all the way up to something called a yotta, which is absolutely massive. It's times 10 to the 24. So basically times by 10, 24 times. It's absolutely huge. You guys, I pointed out nano a little while ago. Nano is not as small as something can get. You can get smaller than that. Picos and femtos and attos and zeptos and yoctos. And seriously, I feel like those words are just made up. Like, that's the sort of thing you can do with SAGEs too. So, here's what you guys need to know. On your formula sheet, does anybody have a formula sheet in your back? There is actually, can I steal Joey Becker's for measures? There is a, so maybe everyone can see. Right in the middle of it, there's this prefix symbol and exponential value. So like atto is minus 18, femto is minus 15, all the way up to tera, 10 to the 12. You guys found that? Okay, those are the ones you need to know. So the first activity I want to walk through then is let's see whether we can convert between different unit types. Okay. Maybe you have some experience with this already, so let's try that. Let's say I gave you 8,000 kilograms. I want you to turn it into grams. First question I have, are we going to have more than 8,000 or less than 8,000? Way more, yeah. The reason being is that a kilogram is a very large unit of measurement, right? And now we're turning it into grams, which is a very small unit of measurement. We're going to have a lot more of the grams, which are small, than the kilograms. So then, however this works for you, you got to figure out what the prefix is. What is the times 10 to the power of a kilo? Yeah, it's times 10 to the 3. So essentially, one way you could write this is 8,000 kilograms. You could say that that's equal to 8,000 times 10 to the 3 grams. Essentially, this thing right here is what your K means. So don't write the K anymore. Write the times 10 to the 3. That's how many grams you have. Well, this will make the number 3 zeros bigger. So the answer is 8,000 with 3 more zeros. That's how many grams it is. Everyone kind of has their own way of making this work in their head. You just need to figure out what works for you. Makes sense? Okay, let's keep up. Meters to centimeters. Should we have more or less? Going from a meter to a centimeter. Which unit is a bigger unit? The meters, right? So then if we're going into the centimeters, which is a smaller unit, we're going to have a lot more of these small little centimeters, right? So this one is maybe a little bit trickier though, because a centimeter is a times 10 to the power of, I'm not even writing that, 10 to the minus 2, right? This one maybe I can't use that same sort of thing I did before though, where you know how I kind of like wrote the times 10 to the thing here? That probably won't work in the same method here. So I just need to recognize that I need to go by 10. So maybe what I'll do is I'll take my 589 meters, and my phone is ringing. Sorry. Hello. Yeah. Yeah. Uh-huh. No. No. Not as far as I saw last night, no. Okay, that would be convenient. That makes sense to me as long as we physically can, yeah. Okay. Okay, thanks. There's a day on okay, you guys figure out how to do this without me telling you? Are we timesing by 100 or dividing by 100? We're timesing by 100. Yeah, the reason why, again, I started with this is that we're going to have more centimeters than meters. So this is going to be 589 centimeters. Even though this is kind of a negative 2 here, in a way, we actually have to go like the other way and move the decimal place and make it bigger still. Seconds into megaseconds. Capital M is mega. Should we have less of them or more of them? Way, way, way less. Okay. Right. So in a way, we just need to know what the prefix for this is. This is a times 10 to the 6. So, I mean, here's another way maybe you'd learn to do this. Take the decimal place and move it over 1, 2, 3, 4, 5, 6. Right, this is going to be 0.098000 megaseconds. That's a lot of seconds. What if they both have prefixes? What if you start with a kilo and end with a, what is that, deci? Is it deci? Okay, so what's the prefix for deci? Let's start with that. Is it 10 to the... Okay, so this is a 10 to the negative 1, and this is a 10 to the 3, right? So how many times do we have to move the decimal place? From 3 to the negative 1? 4 times, yeah. So the only issue we have now, though, is it getting bigger or smaller, right? Is this number going to be 0.0000, let's see, 1, 2, 3, 4, 6, 5, or is it going to be 1, 2, 4, 650? 1, 2, 3, 4. Does that make sense? That's the question now, is are we making the number way smaller or way bigger? Yeah, we need to make it way bigger, right? Because what we have here is a large unit of measurement. We're converting it into a small unit of measurement. So because we're making the units smaller, we're going to have way more of them. Let me say that one more time. If we're making the unit of measurement smaller, we're going to need a lot more of them. Let's just do one more here and then we'll move on. 87.7 amps into a gigamp. Is it getting bigger or smaller? We're going into a very large unit of measurement. And so because we're using large units of measurement, we're going to have way less of them. So we need to move this thing over whatever a gigi is. Is it times 10 to the 9? Alright, so we need to move this over 1, 2, 3, 4, 5, 6, 7, 8. Did I do that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, even more 0. Alright. That's how many gigaamps we have. You guys done this before? Okay. It's something we'll work on. I'm not going to take the whole class to practice just this one skill. If I haven't shown you something that works in your head already where you can wrap your head around it, chat with me later, okay? Because I can show you different techniques. There's different ways to do this. The long and short of it, though, is you're either making a number larger or smaller, right? And it's always timesing by a certain number of tens. Here's an extra slide, but why don't we just move on? Let's move on to our next topic. Which is scientific notation. After a while, it becomes kind of ridiculous to write out a number like this, 149,000,000,000,000. That's crazy. And yet, a number like that is really common in physics because that's how far it is to the sun. So you have a couple of options. One option would be, well, let's just not record it in meters. Let's record it in something different. Let's say I wanted to convert this numbers into kilometers. Well, one way I could do that is a kilo is a times 10 to the 3, right? So if a kilo is a times 10 to the 3, let's pull off 3 zeros and make it 149,000,000,000 kilometers. That'll work. Let's go with a bigger unit of measurement. Let's 10 to the 9 again. 9 was giga. So if I pull off these 3, and these 3, I could say it's 149 gigameters. Sounds fun, doesn't it? So many of you probably know how this is going to work. What we could write instead is 1.49 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we usually leave the decimal place with 1 digit to go. So 10 to the 11. That's another way we could write it. It kind of shortens it up a little bit. What if there's a whole bunch of zeros in front of the number? Negatives on it, right? So here's where that prefix list might actually come in quite nicely. What is times 10 to the negative 9? Is it a nano? It's been a long time since I've done this one. Still learning. If it's a nano, can you guys see how there's 1, 2, 3, 4, 5, 6, 7, 8, 9? I could call this 20 nanoseconds. So I did that real fast. Let me show you one more time. I counted up and I said, look, here's 1, 2, 3, 4, 5, 6, 7, 8. You know how normally you start right here? I just want one more just because. 8, 9. Okay. And then I looked at my sheet and I said, well, a negative 9 is a nano. So now that the decimal place is in this location right here, I said I have 20 nanoseconds. It's not a bad way of changing that. But let's say I don't want to measure in nanoseconds, right? I could say, well, it's actually 2.0 times 10 to the minus 8 seconds. If I make it 20 times 10 to the minus 9 seconds, it's the exact same thing. But then I could take this times 10 to the minus 9 and change it into a nano. So if you ever have like a scientific notation like prefix right here, that's like minus 9, minus 6, minus 3, some of those ones there. You can change the units. Long story short, I need you guys to know how to manipulate units through different, we call them prefixes, I guess. But I also need you to know how to do the scientific notation. So if that's not something you've seen before, chat with me later, okay? And we'll work on it again. Why don't you guys try this one? Give me a minute or two just to see whether you've done this at some point. So convert it to scientific notation. Don't do unit changing like gigas and nanos. Just see if you can throw the scientific notation properly. So the first one is 2.6 times 10 to the minus 6 seconds. Maybe the best way of doing this is just say, well, let's move the decimal place back. 1, 2, 3, 4, 5, 6. I'll stop it between the 2 and the 6. It's a negative because you're going backwards, right? Does that make sense? Okay, another option, I didn't ask you to do this, but another option then would be to say that this is 2.6, and then what's the minus 6? It's micro, right? Micro is that funny looking U. So you could call it a microsecond. That's another way of writing it if that works for you. This one here, move it this way. 1, 2, 3, 4, 5, 6, 7, 8. So you can call it 2.6 times 10 to the 8 meters. Let's say you wanted to change the type of unit though. Do we have something that goes to the 10 to the 8? Sadly, no. So, I mean, here's what you could do. You can move it over one more time just because and make it 0.26 times 10 to the 9. And then 10 to the 9 would then be a giga. You can do that if you really wanted to. So this one here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 9.09 times 10 to the 12 moles. That'll work. Or I need you to be comfortable if, let's say we didn't put the 10 to the 12. Actually, this one I don't know. What is 10 to the 12? Tera? Okay. So, I mean, you could just pull that bit off there and call it a T mole. Teramoles. That'll work too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You could call this 7.92 times 10 to the minus 10 kelvins. This kind of stinks though. Let's say I didn't want to work with this. Let's say I wanted to change the notation. Do I have something that goes to the minus 10? No. What I could do then is go to the minus 9 maybe. So maybe I could not have done this last one here. Stop this here. That would make it 0.792 times 10 to the minus 9. A 10 to the minus 9 is a nano. How are you guys doing on the first four? Is that something you can follow and you can remember? Okay. So last one here. This one's purposefully here. Does it really help shorten the number to write it as 8.01707097 times 10 to the 8 grams? How did that help? How did that make it faster to write it like that? So maybe you can kind of see where I'm going, especially if you look at the next slide. At some point, we need to round. Because we just can't keep every single digit. Right? And so that leads into the next topic. Whenever we measure something, it has what's called a precision. And I use these words a lot. I'm actually a big stickler. I want you to use precision and accuracy in the right spot. So essentially, precision is how many digits do you have? How far can you keep writing numbers and know that the number is correct? Let me give you an example with a ruler here. One of these rulers is way more precise than the other one. This ruler right here, if I asked you to measure where about it was right here, you'd have to go, well, it's more than 2. It's less than 3. And you'd have to guess and say, I don't know, about 2.5. And you're right. But are you very precise? Well, you're precise to the nearest 10. Does that make sense? You have 1 decimal place. This ruler here is way better. Because I know what the next digit is. It's not just 2 point, I don't know. It's 2.1, 2, 3, 4, 5 for sure. And then it's between 5 and 6, so let's call it 2.55. This is a better ruler, it's more precise. Let's say there was a ruler that had even more incremental lines in between. Maybe I could say that this number is actually 2.557. You see where I'm going here? The more digits you have, the more precise it is. Okay. And so a number like these ones we have back here, this is a very precise number because of the fact it has so many digits. We actually call them significant digits. We'll get to that side in a bit. So this is actually a very precise number, but sometimes we don't actually have the tools capable of measuring such a number. And that's where the next word comes in, which is accuracy. Do I have accuracy written down here? I don't. So let's talk about accuracy. Precision is basically how many digits do you have. If you have 1.5793214, that is a very precise number. Accuracy is your instrument calibrated properly? Is your ruler actually set up to be able to measure that? Does that make sense? So accuracy is like correctness. Sometimes I give this example. I'd say that I drove from Lethbridge to Fort Macleod this morning. And so I might have measured my distance to be 50 kilometers. Is it accurate? Yeah, it's pretty close, right? It's about 50K from here to Lethbridge. Am I very precise with that number? Not overly. I was precise to like the nearest 1 kilometer. What if I told you that I drove 50.973124 kilometers? I don't know how I measured it that well, but that's a very precise value. Does that make sense? It's possible, though, to be precise and not accurate. If I told you that I drove 70.57932 kilometers, that's wrong. Makes sense? Because I didn't drive 70-something kilometers, I drove 50-something kilometers. So it's possible to be accurate and not precise. It's possible to be precise and not accurate. Right? One is, do you have a lot of digits? The other one is, are you actually correct? We want both. I learned something really cool over the summer with the Olympics, and so I threw a new slide in here that I haven't on my hat. You guys watch the Olympics? Yeah. Anybody watch this race? This one it blows my mind at first until I learned a little bit more. This is when Michael Phelps actually lost, which like never happens, right? He finished second, but this is the weird thing. He finished in a 3-way tie for second. And so that's my first thought. Maybe you have the same thing as me. How do you have a 3-way tie for second? Like, what are the odds that 3 people all touch the wall at the exact same moment? And so I actually saw a blog post on this, and I learned something, so I'm going to share it with you. They didn't actually touch the wall at the exact same time, right? Because really, someone touched the wall like a nanosecond before the other person, right? That makes sense? Like, although we're going to call it a tie, someone, if we had enough digits, if we had enough precision, they actually would have been able to figure it out. Let me give you an example. Like here, you guys can see down here at the bottom here, the guy who won in 50.39 seconds, right? So why don't we just make up a number here, and let's say that this guy right here was 50.37 seconds, this guy was 50.37 seconds, and this guy was 50.37 seconds. That's why it's a tie. But really, this guy might have been 50.371 seconds, this guy was 50.372 seconds, and this guy was 50.373 seconds. But based on rounding, they all round to the exact same number. Does that make sense? So then the question is, well, why wouldn't we just look at the next digit? Does the technology not exist to see what the next digit is? And actually it does. I mean, we can measure things on a stopwatch very accurately to the nearest, like well past this. We could have gone to, these digits here. And be able to see, no, this guy was shorter, right? But based on where we needed to round, because we're rounding here, stops there. It's actually not based on the limitation of the stopwatch. It's actually based on the pool. When you're racing a 100-meter thing here, everybody has to go exactly 100 meters. But here's the problem. When they make the swimming pool, they're not able to physically make a swimming pool out of concrete and make it so that everybody is going exactly 100.00000 meters. Does that make sense? So the guy who's swimming in this lane right here, he might be racing 100.005 meters. And this guy down here might actually be racing 100.00293 meters. Does that make sense? Like, think about how hard it would be to construct a swimming pool and make it so that the distance from here all the way to the other side of the pool is exactly the same to like 4 decimal places. You know where I'm going here? So even though we're capable of actually on a stopwatch measuring lower digits of precision, it's actually due to the accuracy of the pool. So I want to use those two words differently here. The precision is, yeah, we can find all of these digits for how long someone was. But the pool has not been accurately made to 100 meters because there's a little bit off depending on what lane you're in. So you might actually have an advantage if you're swimming in lane 2 because your lane might just be that much shorter. Does that make sense? So based on that, they decided they always have to round to the nearest 100th of a second, which is why you can have a 3-way tie. If they didn't round to the nearest 100th of a second, you could say that Michael Phelps was faster. But Michael Phelps might have had a slightly shorter lane to swim in, and that wouldn't be fair. Does that make sense? So I learned something over the summer, so hopefully now you guys get it too, as to how it's possible to have like multiple ties in swimming. So quick refresh on these words, because I want to make sure you use them properly. Precision is how many digits you have. When we're measuring Michael Phelps swimming, we could measure just more digits afterwards and say he swam 50.37147 seconds. Okay. But accuracy is it correct? Now, those stopwatch is probably correct. We're very good with measuring time. But it's the size of the pool that was hard to be accurate with. because we might not be traveling 100 meters. One guy might go 100.0 meters. Another guy might be going 100.1 meters. Another guy might be going 99.9 meters. Well, that's not fair, right? The guy who's traveling in the 99.9 meters lanes has less distance to swim. Okay, so now let's get to the whole point of all of this. We need to round at some point. That's a very, very obvious thing in calculations. Is we can't keep all of these digits for forever. So there's a few main rules we need to have when it comes to digits. So hopefully you've heard these at some point before. First rule, if you have a digit between 1 and 9, it counts. If we're going to write down the number 8, it means something. It hasn't been, like, rounded. If you ever have a 0 between 1 and 9, it counts as well. Here's where it actually kind of starts to matter here. If you have a 0 like this, 0.003, how many digits does this number actually have? It has 1 digit. It has this digit right here. And at first that takes a little while to wrap your head around. But I use James Bond as an example, 007. 007 is really the number 7. There's 1 digit there, right? That makes sense? So any zeros on this side of a number, they don't count, even if there's a decimal point. But if we take the time to write zeros over here, it means that they must be considered significant, so we're going to count them. So zeros on this side of a number, they don't count. Zeros on this side of a number, they do count. The last one here, if it's in scientific notation, any digit before the power counts. Let's do some examples, because most of you guys have all done significant digits at some point, right? Okay, not you all. So, how precise is this number? It's precise to the nearest tenth, right? But that's where we cut it off. We cut it off at the nearest tenth, right? How many digits does it have, though? 1, 2, 3. This has 3 digits we consider significant. What about this number? How precise is this number? Is it more or less precise than the previous value? Less precise. Yeah, this went to the nearest tenth of a digit. This looks like we know up to the nearest ones number. That being said, though, it actually still has 3 significant digits. This one, and this one count. This number here is very precise. I mean, we're able to measure to a very, very small unit of measurement. It's precise to the nearest, let's see, that would be the 10th, 100th, 1,000th, 10,000. I'm not even sure I could find you a measuring tool in the building that could measure something to the nearest 10,000. That's incredibly small units of measurement, right? So it's very precise, but in terms of how many digits it has, these zeros in front here, we don't consider them to be significant. They're just placeholders. So there's actually only 2 units. The 3 and the 5, they count. This one. Hazard a guess? No. You'd think it's 2, right? Because there's 2 digits. But this one's a bit of a twist. This one is infinity. I don't know why there's an infinity amount of significant digits here. You can't have a partial 1 egg. Makes sense? Right? Like, you either have 1 egg, or you have 2, or you have 3. Can you really have 3.972 of an egg? Does it really work that way? Okay. So there's one exception here. If you have an item where you really logically can't break it in half, you can't have a partial of it, right? Then, in a way, this is exactly 12. We're not writing this number, but there is exactly 12.0000. There is exactly 12 eggs. There's not 12.001 eggs. There's not 11.999 eggs. It's dead on at 12. And you could write zeros afterwards for forever. Are we going to write zeros for forever? Well, no, that's ridiculous, right? So this would be one exception. If you're talking about a number that like is exact, you can't have a partial. Okay, how about here? How many significant digits does this thing have? Okay, well, these ones all count. So 4, 5, 6, 7, 8, 9, 10, 11. Do these last ones after the decimal count as well? They do, yeah. If we take the time to write them afterwards, they do count. So someone has actually measured out precision. Think of that Michael Phelps thing. If we were to go back here and figure out what the next digits are, I just made some up here. I just said maybe it's 147. But if I take the time to write them in as 000, it just by some stroke of luck must have just happened to land right on the 0, 0, 0 numbers. It could happen. So what does this one have? Is that 13th? What about this one? 6. Okay, scientific notation. Ignore this little guy right here. That doesn't really apply all that much at this point. There are 1, 2, 3 sig digs. This guy? 5? Yeah. This 0 doesn't count. A 0 on that side is not applicable. So there's 1, 2, 3, 4, 5. Again, these ones written on this side here. If we take the time to write out more precision, it means we must know what that value happens to be. We have the capability of measuring it. So that's 5. And then this last one here, the zeros are on this side right here, so there's 3 on that one. Why are significant digits important though? Like, why do we care about all this? Because at some point we're going to have to round. We can't keep writing these digits all the way through the whole time. And at some point we're going to have to round. Just like in the Michael Phelps example, at some point we're going to have to round. In physics especially, maybe more so than any other discipline, you can't be off. Right? Maybe I've told some of you the story before. They wanted to send some sort of, I don't know, rover out to go to Jupiter or something like that. I don't know what planet it was. And they missed by just the littlest bit. But here's the problem. This much off, over the course of thousands of miles, it missed the planet entirely. All due to a rounding error. Does that make sense? If I were to, say how far is it from here to the edge of the desk, and I was off by the littlest bit, it's not the end of the world, right? But if I had to travel from here to Jupiter, and I was off by this bit, that little bit will eventually grow and grow and grow and grow, and you'd miss entirely, right? If you're building a bridge or a building, we can't screw up the rounding. So it's very important to know these digits when we do some calculations. So that's our next slide. We need to know how to add and subtract and then multiply and divide these things. I got the time here, but we're doing great. Yeah, no, okay, so the first thing you need to know is that adding and subtracting has very different rules, very drastically different rules. The rule here is you always go with the least precise number. Let me give you two numbers here, 2.2 and 18.267, blah, 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 blah. One of these numbers is way more precise. Crazy precise. I don't know how you even build an instrument capable of measuring something to the nearest, billionth of a kilogram. But okay, crazy precise. Here's the problem. Although this one has been measured at 2.2, is there a digit that could come after it if we had the ability to measure it? Sure. Right? Just like with the Michael Phelps example, there is a digit that comes afterwards. We just rounded it, but maybe that number was a 1, and maybe this number was a 3, and maybe this number was a 0. But we don't know what those numbers were because whatever measuring tool we used, it was not capable of measuring those values. So the only way to be fair here when combining these values is to kind of cut it off right there. So now when I do my math, this is going to be 20.4. Okay, I can still round them like I normally would. See how this guy right here is a 6? I don't know what number would have gone here. That number could have been a 1 or a 2 or a 3 or a 4 or 5. I don't know what that number would have been. So let's say it was a 0. Well, 0 and 6 would have made this be a 6. Is this going to be more than halfway though? Should I round up or down is what I'm getting at. Yeah, definitely round up. Let me guys close that back really. Right? The reason being is that even though I don't know what this number right here is, this 6 right here means that I'm at least more than halfway. So the correct answer for this would be 20.5 kilograms. That's as good as we're able to round it. That'll do. Just so you guys know, if you want to try it out, so that little crank thing that's in the door there, what we can do is we can turn that, and it'll seal it all the way shut if we need to. So if it's too loud back there, just do that. Does that make sense? So adding, subtracting, very different. You always have to cut it off at whatever the least precise number is. There are more values here if we took the time to measure them, or if we had the ability to measure them. But since we don't know what this number right here is, even though I could measure all these numbers here, I cut it off right there. And then just make sure you round. So since 6 is more than halfway, right? Since 6 is greater than 5, then round it up.
Mr. Fisher?
It's a little different when you multiply and divide. When you multiply and divide, what we do is we go with the least number of significant digits. So this one here is precise to the nearest tenth. This one here is also precise to the nearest tenth. But this one right here only has 2 sig digs. So based on that, our final answer can only have 2 sig digs as well. I'm not going to do multiplication in my head. Someone help me out. Who's got a calculator? 3.8 by 14.6. Any digits after that? Okay, so here's where one of the big issue comes in then. So we centimeters squared. See how this was precise to the nearest tenth? This was precise to the nearest tenth as well. Look at my answer. My answer is now precise to the nearest 100. How is it possible that somehow it became more precise just by putting numbers together? Doesn't that seem kind of illogical? That my one scale could measure to 1 decimal place. My next scale could measure to 1 decimal place. Put those numbers together and somehow I'm precise to the next 2 decimal places? Doesn't that seem like that could cause some issues? So the rule here then is that you only get to have as many as the lowest number of sig digs. This has 2 sig digs, this has 3 sig digs, so this number here only gets 2 sig digs. So I keep the 5, I keep the 5. Is this 4 enough to round up? No. So the answer is 55 centimeters squared. I get 2 sig digs. Some kids, they think this, they might say, hey, 8. 8 rounds up. So if 8 rounds up, it makes this a 5. Hey, 5 rounds up, that makes this a 6. Where's the flaw in that logic? Why can't I say 8 rounds the 4 up to a 5, the 5 rounds this 5 up to a 6, hey, this 6 rounds this up to, well, why does that work? Where's the flaw in that logic? Well, think of it as this, 48. Now it's 48 hundredths. Is 48 out of 100 over halfway? Like 48 out of 100, that's not halfway. Right? Is 4 out of 10 over halfway? No, right? It could be 49999. You can throw 9s on there all the way there, right? But then this would have to be out of like 100,000. Is that over halfway? Darn, it's close, right? But it's not over halfway. So don't make the mistake of saying, hey, this rounds that one up, this rounds that one up, this rounds that one up, this rounds that one up. Hey, it's a 5. Make sure you know how to do your rounding. Okay, quick recap before we do our last little bit here. So I need you guys to know how to do units. That's really important. All numbers should have a unit next to it. You should be able to work with scientific notation. You should know how to convert between unit types, the gigas, the nanos, the kilos. Again, if you need help on that again, like if this was too fast or went over your head, find me, we'll chat more. I'll give you some more strategies for that. I really want you to know the words accuracy and precision. Accuracy is the correctness of the value. If we use a measuring tool, is the tool calibrated properly? Right? If, for example, if I step on the scale, but my dog was also on the scale at the same time and I didn't notice it, and I look at my weight and I go, whoa, I gained some weight. Was the scale accurate? Well, no. My dog got on the scale. It's not an accurate scale. It's precise, though, to the nearest whatever, right? So if I step on the scale and it says, I'll give you a really nice sounding weight, 190. But like, if it says 190, that's to the nearest 1, right? If I go 190.3, it's more precise. 190.357, that's even more precise. Does that make sense? So those are the difference between accuracy and precision. And then last thing, we're now going to start using these numbers. We're always going to have to round. Like rounding is a fact of life. So we want to make sure we do it using a correct set of rules. So the rules for adding and subtracting, we go with the least number of precisions for adding and subtracting. Multiplying and dividing is the number of digits you're allowed to have. So last thing we'll work on then, let's actually start doing some real basic calculations here. Before I get to that though, I'm going to talk about what are called scalars and vectors. So maybe you've heard these terms before here. Basically the concept is, does direction matter or not? If something is a scalar, I just give you a unit. Say I went 100 kilometers. And a lot of times that's really good. Like when I drive, I drove 50 kilometers this morning. It wasn't a very precise number, it's probably accurate. But an even better way of explaining something is to tell you which way you went. If I can give you a direction, that's even more powerful. So long and short of it is, scalar just tells you how far. The vector, which way. So there's a lot of things that we can attach a direction to. For example, right, here's my pencil. How long did it take? let's say a second. Can I put a direction on that? Does time have a direction? Okay, no, I can't really put a direction on that time measurement. But if I ask you which way I threw it, and maybe how far, you might say, well, I threw that about, I don't know, 4 meters. But I threw it 4 meters, I don't even know where we are anymore, north. Does that make sense? So I could put a direction on it. I could even tell you how fast I threw it. I threw it at 3.5 meters per second. Also north. That makes sense. If I asked you how hot it was in the classroom right now, you'd say it's 20.4 degrees Celsius. Can you put direction on a temperature though? So there are some things that logically you can put a direction to, and other things that really, there really doesn't fit a direction for it. So that's scalar versus vector. The way we notate this then, oh, this got screwed up here, is we put a little arrow hat on top of things. So if you ever see a little arrow hat on top of it, it means that we care about the direction. If you don't see it on top, then we don't. So these, I don't know why this got formatted. All these little arrows right here, we're supposed to be right here. Oh, so they're right on there, but they're not right on here. Okay. So let's talk about our first two formulas, essentially. If I ever ask you what a distance is always a scalar quantity, and it's basically how far did you go. So if I asked you how far it was from me to my pencil there, I'd say 4 meters. I have to have a unit, whatever unit happens to be. But I don't give you any sort of direction. The word we use for something with a direction is called a displacement. Put that little arrow hat on top of it. A displacement says it's 4 meters north. Does that work? So we drove from Edmonton to Peace River. You know how like the sign on the side of the road says that it's 500 kilometers from Edmonton to Peace River? You know what I'm talking about there, like the ones on the highway signs? Is that referring to a distance or a displacement? That's a distance, yeah, because it didn't give you a direction. It doesn't tell you that when you're driving from Edmonton to Peace River, you're going northeast. Because really, you're going all sorts of different directions. For a while here, you're going north, what is that, east? Then it looks like you're going directly west for a while, then roughly north for a bit. Now you're going kind of northwest, and you're going directly west. So this road right here, which is say 500 kilometers, that's what the sign says. That one would be a distance, no hat on top of it. I've got my units. We know how far it is, but there's really no direction to it. Let's say though that you could fly, and you didn't choose to go where the road was going. Let's say you went directly from Edmonton to Peace River. Okay, first of all, is it going to be the same distance? Like, is it going to have the same value probably? No, because like if you can fly in a straight line, you can see that that's going to be a shorter distance, right? So maybe according to this one, I might say that it's 300 kilometers, it's shorter. But here's the difference though, I have to tell you which way I'm traveling. So I might say that this is, suppose we put it in like square brackets. That's going like northwest. That makes sense? So straight line distance is often a displacement. I will tell you that if from here to here, I went 300 kilometers northwest. So I can actually give you a direction. If you're just kind of driving wherever the road takes you, that's no longer a displacement because, like I said, here you're going north, here you're going west, here you're going north. For a little while, you're going kind of east here. So distance is this one here. Displacement, with a little hat on top of it with the direction, is the straight line distance. So let's do a really, really basic example. Someone's going to start here. They're going to walk east. They're going to walk back west. We're going to try to find the distance that they travel and the displacement they travel. So let me just actually just walk this out. My starting point. I'm going to go 1, 2, 3 steps this way. 1, 2, 3, 4, 5 steps this way. How far did I walk total if I don't care about direction? I walked 8 meters, right? That's my distance. I've walked a grand total of 8 meters. Now, first thing I should talk about here. Why did I not stop at 8? Why did I do the point zeros? because of the precision and the way that works. 3 meters plus 8 meters, but they were all measured to the nearest tenth, right? We had the ability to measure them to that distance there. So it means I need to continue. That's not right. 3 and 5 gives 8. That makes sense. So make sure you maintain that precision because it still is to the nearest tenth. I went 8.0 meters. But since I was going multiple directions, I was going sometimes east, sometimes west, I don't throw a direction after it if I ask you for a distance. What if I want a displacement? Give this one a try. 2 meters, 2.0 meters. Don't forget that 0.0 meters. And west. From where I started, if I started right here, hopefully you can visually see this, I have now gone 2.0 meters in that west direction. From start to finish, that's where I ended up. So that's the difference between the two. It's subtle, eh? The difference between the two? We're going to have to make sure we really work on terminology at first, because there is a difference between a distance and a displacement. Often in real life, we maybe use well, you probably don't use the word displacement in real life all that often, but if you're not using them correctly, they do mean something different. Okay, that's all I got. Any questions? Okay, so tomorrow we'll do another lesson on motion. In the meantime, just because we're kind of getting started, here's what I'd recommend you take a look at then. What do we got for today? Okay, we have about 20 minutes. So if I go back to my website here, if you're looking for something to work on, maybe you don't need to do a lot of this. I mean, choose how much you need, right? But here's some questions on figuring out how many significant digits there are. Work on that. Or here's some questions on performing calculations with significant digits. Can you add all these numbers properly? Can you times these numbers properly? And then I do have some questions already on motion if you want to give it a try. Like here's one. Raj drives from Olds to Trochu, a distance of 59 kilometers. He then drives west to Sundre, 97 kilometers. What's his distance? What's his displacement? So just the kind of things we just started with. Distance and displacement. So, yeah, I guess for the next 20 minutes, so find something to work on. Maybe printers are up and running, you guys can start printing some stuff. I don't know if that's possible yet. Does that work for today though? Yeah. Okay, I'll stop recording and then I'll chat with you guys over there and lumber for a bit if we can find somewhere to chat. So,